In this example, we will calculate the change in entropy for an ideal gas that first expands isothermally and then is heated at constant volume. Here is the problem. 0.005 cubic meters of an ideal gas at a pressure of 1.02 times 10 to the 5 pascals and temperature 300 Kelvin expands to double its volume isothermally and then is heated at constant volume to 373 Kelvin. The molar heat capacity at constant volume is 12.6 joules per Kelvin per mole, and the gas constant is 8.3143 joules per mole Kelvin. We will find the total change in entropy of the gas. First, we need the amount of substance. We get the number of moles from the ideal gas law at state 1. N equals P1 times V1 divided by R times T1. Substitute the numbers. Now compute the value to get approximately 0.2045 moles. Next, let's build a pressure-volume diagram to visualize the two steps. We place volume on the horizontal axis and pressure on the vertical axis. Step 1 is an isothermal expansion at 300 Kelvin. The curve is P equals N RT over V. We mark state 1 and the end of the expansion, state 2. Step 2 is isochoric heating. A vertical move up at constant volume from state 2 to state 3. Entropy is a state function, so the total change equals the sum over the steps. Delta S total equals delta S1 plus delta S2. For a reversible isothermal step of an ideal gas, delta S1 equals N R times the natural log of V2 over V1. For a constant volume step, delta S2 equals NCV times the natural log of T2 over T1. Now we compute numerically. For step 1, the isothermal expansion, delta S1 equals N R times the natural log of 2. Compute N R, the natural log of 2, and the product. For step 2, the constant volume heating, delta S2 equals NCV times the natural log of T2 over T1. Compute N times CV. Then the natural log of 373 over 300, and multiply. Finally, add the two contributions to get the total entropy change of the gas. Delta S total equals delta S1 plus delta S2. Numerically, this is about 1.178 plus 0.561, which is approximately 1.739 joules per Kelvin. Recap. Find moles from the ideal gas law. Use the isothermal formula N R log V2 over V1, use the isochoric formula NCV log T2 over T1, and add them. Entropy is a state function, so it depends only on the endpoints, not on the details of the path, as long as we compute with reversible steps.